Hello, everyone. Today we are going to continue with solving some problems. We would mostly focus on, again, things like Jordan canonical form, determinant, minimal polynomial, and characteristic polynomial, and things like that. So we would just mostly try to solve some more advanced problems, a little bit more technical, and some of them, they need more interesting ideas to solve them. Um, because at this point I think we have gained some we learned some basics about these things in algebraic geometry, and we can tackle maybe some problems. I want to also introduce a book to you, which I think you can find it online, not just about linear algebra, but in general about the basic undergrad things you need to know in mathematics, like analysis, algebra, linear algebra, calculus, measure theory, a little basic topology, and things like that. So probably, as you know, one of the most important skills for a person who does mathematics, and one of the most important things that I guess all of us hope to gain when we are learning mathematics, is the ability of solving problems, right? So, and you can, I guess, get that, you can learn that, you can get that skill, but just solving problems. So there are some good books that they give you a lot of interesting questions just to think about. And one of the good ones is a book named Berkeley Problems in Mathematics. It's a very interesting book. It has different chapters, like on linear algebra, I think maybe number theory, or maybe that's also part of algebra, calculus, analysis, and topology, other things. And then it has different sections. For example, in linear algebra, it has, I don't know, matrices, determinant, vector spaces, all these things. And in each section, it just has some interesting questions. The questions that you understand the question is not, the statement of the question usually is not very complicated. It's easy to understand. The questions are usually tricky and interesting. They are kind of puzzle form. You can think about them. The good thing is that the book also contains solutions, very, very well written solutions. So you can, if you can't solve the problem, you can go and look at the solutions. So I really recommend this book, now for this course in linear algebra, and also generally for like the other courses you have. You can just pick the questions. I don't recommend looking at the solutions very fast. If you can't solve the problem, you can, yeah, I would do that. So the name of the book is Berkeley Problems in Mathematics. It's written by, if I pronounce correctly, Paolo Souza and Jorge Silva, if I pronounce correctly. And then, so I recommend you just choosing a question, think about it maybe for a day if you can't solve it. And then if you find a solution, you can also look at the solution of the book, because there might be another solution in the book which is more efficient, or maybe your solution is a better one. I guess sometimes even for some questions, there are more than just one solution. And I really used that book for myself when I was an undergrad, and I was attending these kind of mathematical Olympiad contests for like students in universities, undergrads, and things like that. I use this book. It's a good book. So I recommend that. Today, we would look at some of the questions in this book. Okay. So I just wanted to let you know about that. Okay, so let's start with just reviewing a problem from your homework, because I think we did not talk enough about Jordan form, and in your homework you had a question about that. So let's just review that problem first. I noticed some of you have not solved that correctly, and then we would go towards more interesting questions, other questions. So the question in your homework, question number 1 was this. Suppose we have a matrix, let's call that A, equals to 1, 1, minus 1, and 3. And the question was asking for the eigenvalues of this matrix. So find eigenvalues, eigenvectors. It's Jordan form. And also what is find a to the power 50? What is that? Okay, I'm going to solve this one because you already have thought about this one. This was in was a homework question, right? So what is the solution? So as you know, we should start by solving this equation. We should look at determinant of a minus lambda I equal to 0, right? A minus lambda times the identity matrix, which is equal to 1 minus lambda, 1 minus 1, and 3 minus lambda. This is the matrix we would get. Now, determinant of this matrix is equal to 1 minus lambda times 3 minus lambda minus 1 times 1, which is minus 1. And therefore, it is equal to lambda squared minus 3 lambda minus lambda minus 4 lambda plus 3 plus 1, which is lambda squared minus 4 lambda plus 4, right? Now, this can be written as lambda minus 2 squared. And if we set that equal to 0, if you look at this equation, determinant of a minus lambda I equal to 0, we would see that lambda minus 2 is equal to 0. Therefore, lambda is equal to 2. But you should note that here the algebraic multiplicity is 2. So let's call that the algebraic multiplicity. Okay, so that's the only eigenvalue of this matrix. So this is the only eigenvalue of this matrix. Now we want to find the eigenvector. That was the second step. So the second step is to find the eigenvector of this matrix. So eigenvector is a vector like V, such that A times V is equal to lambda times V, which here is 2. So it would be 2 times V. Therefore, it means 1, 1, minus 1, 3 times a vector V, which I would denote the coordinates of this vector by V1 and V2, should be equal to 2 times V, 2V1 and 2V2. So if I do this computation, AV, I would get V1 plus V2 equals to 2V1 and minus V1 plus 3V2 should be equal to 2V2. The first equation, if I take V2 to the other side, tells me V1 is equal to V2. The second equation, also if I take V1 to the other side and V2 to the left side, gives me the same thing. So the only thing I know about this vector, which is kind of enough because we want the direction of the eigenvector, is that the coordinates, the x coordinate and y coordinates are equal. So this any vector like V would be a multiplication of this vector 1 and 1. So this is an eigenvector for this eigenvalue. And the eigenspace would be just the span of this vector 1, 1. Now, we should note that although the algebraic multiplicity was 2, so we notice that the algebraic multiplicity of the eigenvalue lambda equals to 2 was 2, right? The characteristic polynomial is this one, which you can see the degree is 2. So it's not a simple eigenvalue. It's a eigenvalue with degree 2. But the eigenspace corresponding to that is one-dimensional. So the corresponding eigenspace, the eigenspace corresponding to lambda equals to 2 is just the span of this vector, which is one-dimensional. Now, in this case, one might look for the generalized eigenvector. So the next step is to look for generalized eigenvector. What does that mean? So this vector which we found, the vector v, was in the kernel of a minus lambda, which here is equal to times I. Now, a generalized eigenvector is a vector like u, which is in the kernel of this matrix to some non-zero power r. So r is an integer greater or equal than 1. So here in our case, if we look at the matrix we have, a minus 2 lambda, 2i is equal to minus 1, 1, minus 1, 1, right? Now, we found that the vector 1, 1 is in the kernel of this matrix. So I should look at the higher orders, higher powers. So for example, if I look at this matrix squared, it would be minus 1, 1, minus 1, 1 squared, but actually that's just the zero matrix. It has 0 in all entries of the matrix. And we know anything is in the kernel of this matrix, right? This is the zero matrix. Any vector is in the kernel of this one, okay? So here we can pick any vector v. Well, I used v for the other one. Maybe I use v1 for the previous vector and use v2 for this vector. I can pick any vector v2 in the kernel of this matrix, which means everything, but I just want it to be linearly independent with respect to v1, such that this set v1 and v2, they form a linearly independent basis for R2, right? So I can choose any v2 I want, right? So for example, well, maybe the simplest choice is just 1 and 0, and that, of course, is linearly independent with respect to 1, 1, which we already chose. So that's v2. So v1 is equal to 1, 1, and v2 is equal to 1, 0. Now, we are in it's a good time to write down what is the Jordan form of the matrix A. Jordan form of the matrix A. You know, because the matrix A, it has just one eigenvalue, the eigenvalue is 2, and the multiplicity is also 2. The Jordan form can only have, there are only 2 options for the Jordan form. It's either, well, we know that on diagonal we should have the eigenvalue and it has multiplicity 2. So on diagonal we have to have 2 and 2. And here it's always 0. So the only thing which we don't know is that if this matrix is diagonal or not. If it's diagonal, it would be like this. If it's not, the Jordan block would have 1 here. And actually, we already know that this one is the answer, because when we looked at the algebraic multiplicity of our eigenvalue, it was 2. But when we solved the equation AV equals 2V, the number of linearly independent vectors we got was 1. In this situation, we always end up with this form of the matrix. But we can compute that directly too. So how is that? We know that the Jordan form of the matrix A, if I show it with J, is equal to P inverse A P. Right. So I only need to find this matrix P, right? So how can I find this matrix P? What is the value of this matrix P? So if you remember, this matrix P can be constructed using the vectors we found in the kernel or in the eigenspace or generalized eigenspace of our matrix, the eigenvalues of our matrix. So what is the value of P? What should I take for P to be? Well, here the first vector we found was 1 and 1, and the second one we found was I think 1 and 0. And then we can simply just compute J by this P inverse AP, which I wouldn't do that. That's simple and you can do it. And that's pretty good, because when we have that, it means A is equal to P J P inverse. And in order to find A to the power 50, we need to multiply P J P inverse by itself 50 times. Now, the good thing is that all these matrices, P inverse and P in the middle, they cancel each other. Okay, so maybe just in order to be more clear, I would write it down one more factor. So we have this guy times this one times this one times this one, right? 50 times. Now, P inverse P, they cancel each other here. P inverse P, they cancel each other here. P inverse P, they cancel each other here. All these P inverse P's, they cancel each other. So it would be equal to P, J, P, J to the power 50, because then we would end up with J times J times J times J times J, P inverse. So in order to compute A to the power 50, we really need to compute J to the power 50. And that's a simple task. Computing this matrix 2, 1, 0, 2 to the power 50 is not hard. We can actually, this can be done by kind of induction. So the idea usually is to look for pattern. So J to the power 1 is equal to 2102. If we compute J squared, we would see it is equal to 440 and I think 4 again. Yes. So we can look at J cubed. So what is J cubed? It would be 808, and here we would get 12. And then if you just look at a few examples, you can guess what the pattern is. So the pattern is J to the n is equal to 2 to the n, 0, 2 to the n, and I think n times 2 to the n minus 1. Let's see if that's correct. So for example, when n is equal to 3, this pattern tells us J cubed is equal to 8. 3 times 2 to the 2 squared, which is 4, 0, 8, which is correct, which is what we saw here. And as soon as you guess the pattern, you can prove it by induction. So, well, you check the base case, and then in order to prove by induction, we should prove j to the k is equal to 2 to the k, k to the k minus 1, 0, 2 to the k. That's what we need to prove. And that's fairly simple because the assumption of induction tells us j to the k minus 1 is equal to 2 to the k minus 1, k minus 1, 2 to the k minus 2, 0, 2 to the k minus 1. And j to the k is just multiplying this thing by j. And then a simple computation, a multiplication, shows us that we can prove this fact by induction. Okay, so that's how you should do this problem in your homework. Okay, so the question I would like you to think about for a few minutes is this one. Suppose A is an n by n real matrix. Okay, and so we can think about this matrix as a linear map from Rn to Rn, right? So for any given vector v, you just multiply that by this matrix A. Suppose AT is the transpose of this matrix, and that also gives you a linear map from Rn to Rn. Now, if we multiply these two matrices, we get another matrix, A transpose A, and that's also can be thought of as a linear map from Rn to Rn. Okay. Now, the theorem we want to show, we want to prove that A transpose A and A, they have the same range. They have the same range. In other words, the image of these two linear maps inside Rn, inside the codomain, coincide. They have the same range. Okay, think about this one for a few minutes. So in general, how do you think we should try to approach this question? We have two linear maps, and we want to show that they have the same range. How can we do that? Give me your idea, not necessarily the final answer.
My thought, which might be very wrong, was that we know that the rank of A is something, less than or equal to n.
Mm-hmm.
And we know that for a linear map, the column rank is equal to the row rank.
That is correct.
The column rank of AT or A transpose is going to be equal to the column rank of A. So maybe
that's correct.
Something that the combination of the two or the composition would still have the same rank as A would. I don't know if that proved that they'd have the same range, but you'd prove at least that the ranges had the same dimension.
Yes, that's very good. So yeah, this is a very actually good approach. Why? So we want to show the range of two maps are equal. Let me just make sure I'm recording. Yeah. So the range, we want to show the range of two linear maps are equal, right? So actually what you said was kind of in the direction of proving that the dimension of a range of A transpose A is equal to dimension of range of A. That's interesting. Maybe I'm not sure. Maybe it's better. Let me just think for a second to make sure there is nothing wrong with the question.
I think if A equals 0, 1, 0, 0, then this doesn't hold. But
yeah, so I should actually, okay, I should rephrase the question slightly differently. I'm sorry. So your approach is correct, but there is a small mistake in the question. So suppose A is an n by n real matrix from Rn to Rn. A transpose is another real matrix Rn to Rn, and therefore A transpose A can be considered as a linear map from Rn to Rn. What is correct is that A transpose A and A transpose, they have the same range. So that's what we need to prove. Yeah, thank you for for understanding that. Yes, so now that makes sense. So I want to show these two as linear maps from Rn to Rn. I want to show they have the same range. So the idea is usually like this. Usually you have two linear maps. You want to show they have the same kernel or the same range. One strategy, one approach is to show one of them, their kernel, for example, if you want to show they have the same kernel, is a subset of the kernel of the other one. Or if you want to show they have the same range, you should show the range of one of them is subset of the range of the other one. And later you would prove the dimension of the range of both of them are equal, or the dimension of the kernel of both of them are equal. And we know when we have two subsets, one subset of the other one, when they have the same dimension, they have to be equal, okay? So here, for example, look at A transpose A. What is the range of that? The range of this matrix means, look at all the vectors of this form, A transpose A V for any V inside Rn. All of this thing is its range, right? The point is that A times V is something. It's a vector, right? A is an n by n matrix. V is a vector. If I multiply A by V, I would get another vector. So I can show that by U. So this thing is actually equal to A transpose U. And the vectors of this form, A transpose U, they are in the range of A transpose, right? Do you agree? They are inside the range of A transpose. Anything of this form, A transpose U, is something in the range of A transpose. So this shows us that the range of A transpose A is a subset of range of A transpose. More than that, both of these things are vector spaces, so it's a subspace. Now we know if we have two subspaces, if they have the same dimension, they have to be equal. How can I show these two have the same dimension? So we know one theorem which helps us to prove these things, right? This is the rank nullity theorem, or maybe use different name to address that. So the point is that for the matrix A, we know dimension of kernel of A transpose plus dimension of the image or range of A transpose is equal to n, the dimension of domain, which is Rn, right? So what can I say here? What does it tell me? How can I relate this one to A transpose A? I know, okay, someone wants to give an answer?
I think that the matrices A and A transpose have the same column ranks, and so the dimension of the kernel of A transpose is going to be the same as the dimension of the kernel of A.
That is correct. That is true. So, well, let's write down first thing, because we want to compare it with, I would use what you said. We want to compare this with A transpose A. So I can think about A transpose A itself as a linear map. So I can write down the same equation for A transpose A. What do I want to do is I want to show these two quantities are equal. What I want. What we want. Right? We want to show these two quantities are equal. So if I can show these two quantities are equal, if I can show these two quantities are equal, then using these equations, because of course n is equal to n, the right-hand sides are the same. Therefore, the dimension of range of A transpose would be equal to dimension of range of A transpose A. So it is enough to show, dimension of kernel of A transpose is equal to dimension of kernel of A transpose A, right? Now, dimension of kernel of A transpose. Look at kernel of A transpose. What do we know about the dimension of kernel of A transpose? You mentioned that it's related somehow to dimension of kernel of A. I'd like you to think about this thing. This is kind of important and basic. How can we relate the information of A to information of A transpose? Dimension of the kernel, dimension of kernel, the dimension of range, and things like that. How are these quantities related? So think about that maybe for a minute. So what do we know about these? So the idea is usually, I'm sure you're familiar with that, to compare the rank of A transpose and the rank of A. Actually, it was in the quiz you had recently. It's kind of related to that. So what is the rank of A and what is the rank of A transpose? Does anyone want to give an answer?
The dimension of the range of each.
Yes, but looking at the matrix, there is another interpretation for the rank of a matrix. It's the number of, does anyone know that?
Linearly independent columns.
That is correct. Well, if we take that as definition, the rank of A transpose would be the number of linearly independent rows, for example. And we know the number of linearly independent columns is equal to number of linearly independent rows, right? Therefore, the rank of A should be equal to rank of A transpose. On the other hand, kernel of A transpose, for example, this one, is equal to n minus rank of A transpose. And kernel of A is n minus rank of A. If rank of A is equal to rank of A transpose, therefore n minus those numbers should be equal. So kernel of A transpose, I'm sorry, I mean the dimension. Yeah, the kernel is not correct number here. I mean the dimension of that. Let's call it nullity. I just mean the dimension of the kernel. They should be equal, right? That's something we know. Okay. So having that in mind, in order to prove dimension of range of A transpose A is, I want to prove it's equal to dimension of range of A transpose. But because range of A transpose has the same dimension as range of A, it is enough to prove this equation, this equality is enough to prove dimension of range of A transpose A is equal to dimension of range of A. And because these numbers are equal to n minus dimension of kernel of A transpose A, and this one is equal to dimension of n minus dimension of kernel of A, it is enough to show dimension of kernel of A transpose A is equal to dimension of kernel of A. So this is the only thing I need to prove. Okay. Now, the interesting thing is that not only this is correct, but more than that, actually, kernel of A transpose A is equal to kernel of A. That is correct. Therefore, obviously, the dimensions are also equal. Why is that true? So if I want to prove that, I should show that kernel of A is a subset of kernel of A transpose A, and I should show kernel of A transpose A is a subset of kernel of A. It has 2 steps. So let's try to prove the first step. Take a vector v in kernel of A. It means AV is equal to 0. Of course, if I multiply both sides by A transpose, it means A transpose AV is equal to 0, which means V is in the kernel of A transpose A. So we have the first statement. Kernel of A is a subset of kernel of A transpose A. Now let's try to prove the second one. Suppose we have a vector V inside kernel of A transpose A. So A transpose A times V is equal to 0. Okay, that's correct. Now there is a very interesting fact about inner product of vectors and matrices. So let's write down here a little fact. For any 2 vectors U and V any 2 vectors, and any matrix A, we can multiply, say, A by U and then compute its inner product by V. Okay, there AU is a vector, V is a vector, we can compute the inner product. This inner product is equal to the inner product of U and A transpose V. Okay, that's a simple fact. Actually, it's you can just write down the definition for inner product on both sides and you would see that.
We've proven this in lecture.
Sorry?
I think we've proven this in lecture.
Oh, that's great. So I want to use that. So look, if A transpose AV is 0, if I look at its inner product with V itself, the result of inner product of these 2 should be 0, because this vector is 0, inner product of 0 with anything else is 0. But this formula here tells me I can take A transpose to the other side, but then it would become A, right? Because if I take A transpose to the other side, it should become A transpose times V. We can move matrices to the other side. We should always apply 1 transpose to them. So it becomes A transpose. And of course, A transpose is just A. Inner product of a matrix, of a vector AV by itself is 0. Do you remember one of the properties of inner product was that if inner product of something with itself is 0, it has to be 0. So if inner product of AV with itself is 0, AV has to be 0. It was one of the properties of inner product. So V is in kernel of A. So we started with a vector in kernel of A transpose A. We showed that vector is in the kernel of A. So kernel of A transpose A is inside kernel of A. When we have both of these things, it means kernel of A is actually equal to the kernel of A transpose A. If they are equal, their dimensions are equal. If their dimensions are equal, therefore, by this now rank nullity theorem, dimension of their range for both sides are equal. So the dimension of range of A transpose A is equal to dimension of range of A. But on the other hand, we know dimension of range of A is equal to dimension of range of A transpose. So dimension of range of A transpose A is equal to dimension of range of A transpose. On the other hand, 1 is the subset of the other one, sub vector space of the other one, so they have to be equal. So finally, that shows the range of A transpose A is equal to the range of A. Okay, is there any question here? Okay, if not, let's move on. This question is from the book. I told you, actually, it's an interesting question. So let's look at another question from the same book. It is also a very interesting question. Suppose P and Q are two n by n real matrices. Okay. Suppose P squared is equal to P and Q squared is equal to Q. Okay. Also suppose 1 minus P plus Q, by 1 I mean the identity matrix, is invertible, is an invertible matrix. Okay. Now prove P and Q, they have the same rank. Prove rank of P is equal to rank of Q. Okay, think about this one. Please don't look at the solutions. It's quite interesting. I also like thinking about these questions. Just try to think about it for a few minutes. Okay. Okay, does anyone have any idea on how we can prove this fact? There is a little interesting statement, which I would write it here as a hint. If A is an invertible matrix, say n by n, and B is just another n by n matrix, rank of B is equal to rank of AB. Equal to rank of BA. Let's try to use this fact somehow in this question. How can we use this statement here? Yeah?
We could multiply I minus P plus Q by either P or Q. We know that the squares was from the original matrix, and the matrix times I is also the original matrix, so they cancel out.
Mm-hmm. That's great. Yeah. So if you want to use this hint that if you have a matrix n by n, if you multiply it by another n by n matrix which is invertible, the rank does not change. We can use this fact here. So here our invertible matrix is this one, identity minus P plus Q. So this lemma here tells us the rank of this one is equal to the rank of P times this matrix, which would be P minus P squared minus PQ, right? On the other hand, we know the assumption is that P squared is equal to P. So this is the same as rank of P minus rank of P minus PQ. They cancel each other. We end up with rank of minus PQ, which is equal to the rank of PQ.
Wait, isn't the theorem that the rank of the not necessarily invertible matrix is the rank of the invertible times the not necessarily invertible? So
oh, sorry. Yeah, that is correct. Sorry, I made a mistake. Let's erase that to write it again in order to prevent any confusion. So if we want to use this lemma, we know rank of a matrix. Here we are multiplying. We want to multiply by matrix B is equal to rank of P times identity minus P plus Q, which is equal to the rank of P minus P squared minus PQ. And because P squared is equal to P, these two would cancel, and this is equal to the rank of PQ. Now we can do the same thing with Q. The rank of the matrix Q is equal to the rank of this matrix, I minus P plus Q, the invertible matrix, times Q, which is equal to the rank of Q minus PQ minus Q squared. Now, these two would cancel each other, and this is equal to the rank of PQ. I made a mistake. I shouldn't have multiplied. Oh, no, that's correct. It is equal to the rank of PQ. Great. On the other hand, of course, rank of PQ is equal to the rank of PQ. Therefore, if rank of PQ is equal to the rank of Q and rank of PQ on the other hand is equal to the rank of P, rank of P should be equal to the rank of Q. And that's what we wanted to prove.